Hello, my name is Pavel Pomzov and I'm doing my data project on forest area and CO2 emissions. So what is forest area and what are CO2 emissions? Forest area refers to a large expanse of land primarily covered by trees with a high density of trees and a significant amount of canopy cover. CO2 emissions refer to the release of carbon dioxide gas into the atmosphere. CO2 emissions usually occur when there are transportation, industrial processes, electricity generations, deforestation, other land use, and burning of fossil fuels. Some negative effects of CO2 emissions is that they affect global warming, and the release of CO2 emissions makes the planet warmer by trapping greenhouse gases. Sea levels may rise and the food supply may get disrupted. The data that I will use for this project was collected from the World Bank for forest area and global change data for CO2 emissions. Forest area is calculated from satellite data, while the CO2 emissions are calculated in various ways, such as carbon tracking tools. For example, NDIR is a carbon sensor that detects CO2 molecules in a sample of gas using an infrared lamp. The data is collected from 2000 to 2022, which is global data representing the whole world in forest area and CO2 emissions. I'll be using a linear regression t-test to see if the forest area decreases as CO2 emissions increase, basically finding if there's a negative relationship between these two variables. This is my data. I'll be using data from the World Bank and from global change data showing the forest area in millions of square kilometers and annual CO2 emissions in billions of tons. The data is quantitative and continuous because our data can be counted and can take the form of any number, including decimals. The sample is the yearly data sample points from 2000 through 2022, which are the years where both forest area and CO2 data are available. The population we're interested is in all recorded yearly values of CO2 emissions and forest area in the world. By analyzing the sample, we aim to understand the long-term trends and relationships that may apply more broadly. In this analysis, the explanatory variable is CO2 emissions, measured in billions of tons, and the response variable is forest area, measured in millions of square kilometers. Here's a graph of the data, as well as the equation for y hat, the values for r squared and r, and the variables for y hat and x. Y hat is the predicted amount of forest area in millions of kilometers, and x is the CO2 emissions. With the the equation for y hat, r squared and r are listed on the screen. For the linear regression t-test, b is our beta, which is the average change in forest area in millions of kilometers per every increase in CO2 emissions in billions of tons in the world. The null is that beta is equal to 0, and the alternative is that beta is less than 0. The significance level is alpha is equal to 0.05. The assumptions follow. The distribution at E at any particular x has a mean value of 0. The standard deviation of V is the same for any particular value of x. The distribution at E at any particular x is normal, and the random deviation of E1, E2, E3 all the way to En are independent of one another. For our test statistic, b will be the slope and SB will be the standard error. In our case, with our data, b is equal to negative 0.900062 and SB is equal to 0.100387. The test statistic will be b divided by SB, or negative 8.9659204. The p-value is 6.31938 times 10 to the power of negative 9, which is very small and very close to 0. Since the p-value is very close to 0 and is approximately 0, which is less than alpha is equal to 0.05, we reject the null. We have convincing statistical evidence that there's a negative linear relationship between forest area in millions of kilometers in the world and CO2 emissions in billions of tons in the world. For the other part of my project, I'll be answering these two questions. How strong is the relationship between CO2 emissions and forest area in the world between years 2000 and 2022? And what is the predicted forest area in millions of kilometers for a given 40 billion tons of CO2 emissions? I'll be using the same data as I mentioned above, where from the sources World Bank and the Global Change data. The data is quantitative and continuous. The sample is the points 2000 through 2022, which are listed above. The population is all recorded yearly values of CO2 emissions and forest area in the world. And the explanatory variable is CO2 emissions in billions of tons, and the response variable is forest area measured in millions of square kilometers. For these questions, I'll first plot my data in order to find the linear regression model that will work in order to predict how much forest area there is based off of the CO2 emissions, or the x value. When plotting, I found that the equation for I found the equation for y hat, and I also found the values for r squared and r. For this equation, y hat is the predicted amount of forest area in millions of kilometers, and x is the CO2 emissions in billions of tons. There's a strong negative linear relationship between CO2 emissions in billions of tons and the amount of forest area in millions of kilometers. 79.29% of the variability in forest area in millions of kilometers can be explained by its approximately linear relationship with CO2 emissions in billions of tons. This also means for every increase in 1 billion tons of CO2 emissions, there will be a predicted decrease of 0.0497406 million kilometers of forest area. Using our linear prediction model, we can predict the forest area in millions of kilometers for x value of 40, which is when there are 40 billion tons of CO2 emissions. To do this, we simply plug 40 into x and predict y hat. But by plugging in 40 into our x, we get a predicted forest area of approximately 40.430776 million kilometers of forest area. Reflection. What went well with this project was that I was able to find a strong negative correlation between forest area and CO2 emissions in the world. But what didn't go as well is that there could have been a possibility for other environmental factors that may have influenced the relationship. What should the listeners do? Based on the study's findings, listeners should recognize the vital relationship between preserving forest area and managing carbon emissions. While correlation does not specifically prove causation, the inverse relationship suggests that maintaining and expanding forest coverage can be an important part of climate strategy. Individuals can take action by supporting reforestation programs, reducing paper and wood waste, and advocating for legislation that protects public lands and forests. On a larger scale, governments and corporations should integrate forest preservation into their environmental policies and emission reduction plans. Limitations and errors. A limitation in this project that could have involved the accuracy and consistency of the data. The forest area and CO2 emissions were obtained from a database, which may rely on different measurement methods or estimation techniques across different years. If the way data was collected changed over time, for example due to improved technology, this could introduce inconsistency or error into the dataset. There are also potential for other confounding variables that were not accounted for in the study. Forest area is affected by a wide range of factors, including natural disasters, government policies, reforestation programs, economic development, and land use changes. Possible future studies. This study focuses on the relationship between CO2 emissions and forest area in the United States from 2000 to 2022. One possible direction for future research is to extend the study into specific countries instead of the whole world. Different nations have different environmental policies, and therefore it could lead to varying trends in the relationship between CO2 emissions and forest area. In addition, future studies could explore nonlinear relationship. While the study uses linear regression, the true relationship between forest area and CO2 emissions may be different over time. For example, CO2 emissions could initially increase rapidly with deforestation, then level off or even decrease due to policy shifts. Exploring exponential, logarithmic, or polynomial models could help determine whether a different type of model provides a better fit for the data. Here is my works cited, and I would like to thank all of you for listening to my presentation. Thank you.